Welcome to today's Explainer. We're jumping right into something absolutely mind-bending, the darkest, most terrifying, and honestly, the most captivating phenomena in the cosmos, black holes. As your cinematic AI guide today, I want you to just settle in. We've got some incredible 3D animated scenes lined up to transport you across space and time, to witness the violent birth, the bizarre anatomy, and the impossibly distant death of these cosmic titans. So let's get right into it. Black holes are the universe's dividing by zero error. I absolutely love that quote. It hits the nail on the head because, frankly, they don't seem to make any sense at all. They're these strange spots in space where our entire fundamental understanding of math and physics just breaks. The rules literally do not apply. But to even begin to wrap our heads around how an impossible object like this exists, we really need to rewind the clock and look at how they're actually born. Act 1. Birth from a dying star. Okay, so the violent origin of a black hole actually starts with something incredibly delicate and beautiful. Long before there's a region of absolute darkness, there is a massive star. We're talking a massive glowing collection of mostly hydrogen atoms, all pulled together from giant cosmic gas clouds. And what's happening here is a high-stakes cosmic tug of war. On one hand, you have gravity. The sheer mass of the star is constantly trying to crush it inward. But on the other hand, deep in the star's core, nuclear fusion is smashing hydrogen atoms into helium. That releases a massive amount of energy pushing outward against gravity. And as long as that fusion keeps going, the star stays stable. It's this perfect burning equilibrium. But, it can't last forever. Now here is where the unstoppable algorithm of stellar death kicks into overdrive. From massive stars, way bigger than our own sun, the heat and pressure are so intense they start fusing heavier and heavier elements. Hydrogen becomes helium, then heavier stuff, all the way down the line until they hit iron. And here is the fatal flaw. Fusing iron doesn't create energy, it actually absorbs it. So that outward push, it just stops. The balance completely breaks. Instantly, gravity wins the tug of war. In a fraction of a second, the core implodes. It literally collapses inward at a quarter of the speed of light, packing more and more mass into the center until, boom, it triggers a catastrophic supernova explosion. So what exactly is left behind when the dust clears? Act 2, Anatomy of the Abyss. Let's slow things down a bit to an eerie, deliberate crawl. If that original star was massive enough, the imploded core doesn't just stop at becoming a really dense neutron star, it completely collapses in on itself. The first thing we encounter is the event horizon. If you were looking directly at a black hole, this pitch black sphere is what you'd see. It reflects absolutely nothing. It is the ultimate absolute point of no return. Seriously, once you cross this boundary, the gravitational pull is so intense that to escape, you would have to travel faster than the speed of light. And since nothing can go faster than light, escape is quite literally impossible. You are trapped. But here's the crazy part. The event horizon is really just the shadow. The actual whole part of the black hole, that's the singularity. It is an infinitely dense point in space. Just think about that for a second. All the massive weight of that collapsed star, all of it, concentrated into a single solitary dot, with absolutely no surface area and zero volume. We honestly don't fully understand it yet. It's that mathematical anomaly, that dividing by zero error we talked about earlier. Just this profound, terrifying mystery sitting right there in the absolute dark. Act 3, Falling In, your final moments. So, what if you actually decided to visit one? Let's hypothetically take a trip in our 3D simulation and plunge right into the darkness. Now, quick side note, black holes don't just suck things up like giant space vacuums. If we magically swapped our sun for a black hole of the exact same mass, Earth would just keep orbiting it like normal. We'd freeze, sure, but we wouldn't get sucked in. But if you purposefully steered your ship straight toward the event horizon, things get super weird, super fast, thanks to extreme gravity warping time. Think of it from two very different perspectives. From the viewpoint of a safe outside observer watching you, you would seem to slow down as you approach the abyss. Time literally passes slower for you. Eventually, to them, you look like you just freeze completely in time, turn a faint red, and slowly fade away. But from your perspective, you don't feel slow at all. Instead, as you look back out at the cosmos, you watch the rest of the universe play out in fast forward. It's as if you're watching the entire future unfold right before your eyes. But your sightseeing tour ends pretty abruptly once you actually cross that event horizon. Physics essentially gives us two theoretical options for your final moments. And I gotta warn you, neither one is getting a 5-star review. Basically, you get to choose between a quick death or a very quick death. Let's look at the quick death first. Inside the event horizon, space is curved so insanely hard that every possible direction just points straight toward the singularity. It's like walking down a dark hallway where the walls are magically closing up right behind your heels with every single step. And because the mass is so concentrated, the gravity pulling on your feet would be millions of times stronger than the gravity pulling on your head. This literally pulls you apart. Your cells tear. Scientists actually call this process spaghettification, which sounds fun, but it means you're stretched out more and more until you become a hot stream of plasma, literally just one atom wide. So yeah, ouch. The alternative theory is the very quick death.
In this scenario, the exact moment you cross the event horizon, you hit a blistering wall of energy, a firewall, and your existence is just terminated in an absolute instant. No stretching, no plasma stream, just a sudden, violent, immediate full stop to your biology.
Act 4, Stellar versus Supermassive Monsters.
Now let's pan our view back from the human scale for a second, because not all black holes are created equal. They come in these terrifyingly different sizes that totally dictate how your descent would actually go. First, you've got stellar mass black holes. These might have the mass of a few stars, but they're crammed into a diameter the size of a mere asteroid. The gravity gradient there is so sharp you'd be spaghettified before you even reach the event horizon. But then, there are the supermassive black holes. These are the absolute gargantuan monsters sitting at the center of pretty much every galaxy, just feeding on stars for billions of years. Ironically, because they are so gigantic, you could actually cross the event horizon of a supermassive black hole and survive for a little while before you hit the singularity. The cosmic rule of thumb here is simple. The further away you are from the singularity, the longer you actually live. To really grasp the sheer scale of a supermassive black hole, I want you to just look at this number, 40 billion. 40,000 million. Let that sink in. That is the solar mass of S50014 plus 81, which is the absolute largest supermassive black hole known to humanity right now. Let's ground this mind-boggling scale for a minute. S50014 plus 81 is 40 billion times the mass of our sun. It measures an unbelievable 236.7 billion kilometers in diameter. If you want to visualize that in our own solar system, that is 47 times the entire distance from our sun all the way out to Pluto. Imagine a perfect sphere of absolute consuming darkness, spanning 47 times the width of our entire solar system. It has just been sitting there, feeding on the cosmos for billions of years. It feels completely eternal, completely unstoppable. Act 5, Death by Hawking Radiation. But here's kind of a comforting, if maybe a slightly melancholic truth. Even these seemingly eternal titans are going to die eventually. To see how a cosmic god bleeds out, we have to leap unimaginably far forward into the future. You see, a black hole doesn't die with a bang. Well, at least not initially. It dies with a whisper. We call this process Hawking radiation. The quantum mechanics here are fascinating. Empty space isn't actually empty. It's practically boiling with these virtual particles that constantly pop into existence in pairs, only to immediately smash back together and destroy each other. But if this happens right on the absolute knife edge of the event horizon, one particle gets sucked in, and the other actually manages to escape and become a real particle. So particle by particle, the universe is essentially stealing a tiny fraction of the black hole's energy back over eons and eons. This incredibly slow energy leak causes the black hole to evaporate. And the wild thing is, as it shrinks, the whole process violently speeds up. Let's track its final timeline. By the time this massive beast has shrunk down to the mass of a large asteroid, it's radiating energy at around room temperature. When it shrinks to the mass of a mountain, it's radiating with the blistering heat of our sun. And then, that very last second of its life, the evaporation accelerates so intensely that the black hole completely explodes with the unimaginable energy of billions of nuclear bombs going off all at once. But I have to be clear, this evaporation process is so slow, it totally defies human comprehension. For the biggest supermassive black holes, complete evaporation will take up to a Google years. A Google. That's a 1 followed by 100 zeros. When that final, brilliant explosion finally lights up the dark, erasing the very last black hole from existence, there won't be anyone around to see it. Our universe will have expanded, cooled off,
and become completely uninhabitable long, long before that ever happens. And so that brings us to the end of our explainer, but it leaves us with a pretty profound lingering question. If the universe's ultimate fate is just this silent evaporation, if even the most terrifying, indestructible monsters of gravity eventually fade into absolutely nothing, what other incomprehensible mysteries are hiding out there in the dark right now? The cosmos is vast, it's strange, and it is wondrous. Keep your eyes on the stars and your mind open to the impossible. Thanks for joining me, and until next time, keep exploring.